Okay, so here is sort of a graph that displays all the changes over time of the action potential. What's actually going on, across the membrane in a neuron? This action between the potentials, where we're changing the permeability of the membrane, allowing for sodium and potassium to pass back and forth, and altering the membrane potential, the voltage, across the membrane as this process continues. So on the left side of this, particular graph here, you can sort of see um, what's called potential difference, right? This is the charge difference inside versus out. And you can note at, time zero or over, before the 1 millisecond point there on the, this axis here, we're at around minus 65. So we're at the resting potential, right? And then it's showing, if you look at that voltage change line, the dark line, it's showing it go up towards zero. So zero is higher, basically on this graph. So it's working its way up towards zero. So it's going from minus 65 to minus, 60 to minus 55. What we are doing here, of course, is depolarizing. And the depolarization can happen in many ways. Again, remember, you could press on something and open channels that let sodium in, because it'll be driven by the concentration gradient and electrical forces from the outside of this cell, this afferent, this tactile mechanoreceptor, in. And that would depolarize it because you're bringing positive sodium ions from the outside in, right? Or it could be, again, you've got, a synapse, right? You got a neuron releasing, let's say, an excitatory neurotransmitter here, and then it's going to bind to a specialized receptor. We'll be talking about these very important receptors that let ions go through them. They're called ionotropic. We'll talk about this later, but it's going to twist open in response to the binding of that neurotransmitter to allow for sodium to come in, and sodium will come in and depolarize, this next cell. So you're seeing that initial rise to from minus 65 in the voltage changes line, the V line right there. That's a depolarization caused by something, right? And then all of a sudden you hit the threshold, right? And then you've got on this other side here, right, on the right side of the graph, you've got the conductance. This is, a measure of just how permeable is the membrane to specific ions, and how many ions are sort of moving from one side to the other. And you can sort of see this G, the GNA, that's the sodium conductance, like how much sodium is able to pass the membrane. Really, it's effectively sort of zero at minus 65 because you've only got a few leakage channels to let sodium go across. But when you hit that threshold potential of minus 55, right, when you depolarize in some way to that threshold, well, the voltage-gated sodium channels open, right? And suddenly you've got a lot of conductance, a lot of sodium. So that's that rise there. And that's actually what's serving to lift the voltage line, right? From, minus 55 at threshold all the way up to about positive 20, transiently. And then you see, the GNA, the conductance of sodium, drop dramatically. Well, that's due to a physical change, right, in the voltage-gated sodium channel in response to changes in the voltage. Minus 65, it's like this, right? Minus 55, it opens, and then you see the G line, the conductance go up. And then, about a millisecond later, this receptor is still responsive to the changing voltage, right? So it shuts again. And so the sodium can't move. So the conductance drops back to zero. And remember, I suggest when all that sodium comes inside and it's suddenly very, very, positive on the inside, right? Let's say right here at the axon hillock, right? And there's a hell of a lot of sodium right in this spot. Well, it's going to want to move out of that area. So it starts working its way down towards the next segment of membrane where, it's going to be at the resting potential. Where you've got no sodium because it's all kicked out by the pump, and the membrane's not permeable. There's no open voltage-gated sodium channels there yet, and where it's electrically negative because it's still at the resting potential at minus 65. So it'll move in that direction, further depolarizing as it goes. So as it leaves, right, you see the voltage line drop, right? It drops down. It's also dropping because you should note also there's this potassium conductance sort of line rising and then falling, right? Well, initially, um, it's going to, potassium will be leaving. Remember, the concentration gradient force is winning, but it's still opposed by the electrical force. But as you move that voltage change line up to positive 20 because of all the sodium that rushed in, well, now it's positive on the inside. So not only do you have, a lot of potassium on the inside, so it wants to go out from the concentration gradient force, but you also suddenly have it electrically positive. So it wants to get out of there because it's repulsed, by positive charges because of the electrical force. So you'll see its rate of conductance will increase. And as you move the positive potassium from the inside of the neuron to the outside of the neuron, well, that voltage line is going to continue to drop, right? In fact, it drops back to our polarization level for the resting potential of minus 65, right? But it continues. It actually drops. You can see it drop below. It actually has what they call a refractory period because it gets a little hyperpolarized. And then, as the continued operation of the pump works, et cetera, you're going to have it sort of return again to the resting potential of minus 65. So this is sort of the time course of the action potential, and it illustrates, sort of in one image, like the changes in both the voltage line that occur and the underlying, conductances, the channels that are opening and closing to allow specific ions to, move back and forth and generate action, between the two potentials.